last thing that we'll do in this lecture is prove the second part of the Sylow theorems. So what does that say as a reminder? For each prime p that divides the order of G, it says that all of the Sylow p subgroups are conjugate to each other. So from the first part, we know that there's always at least one Sylow p subgroup. If there's exactly one, this doesn't say anything. So what we're going to do is suppose that there are Sylow p subgroups p and q, and we're going to show that q is a conjugate of this subgroup p by actually writing q equals g inverse for some element g. The big idea is going to be a group action, but it's not the same group action from the previous proof. So we're going to consider the action of q on the set of left cosets of this subgroup p in G by left multiplication. All right, so what do we know about this action? Q is a finite p group, so we can apply this fixed point congruence, which says that the size of our set, the number of left cosets of our subgroup p inside of G, is congruent to the number of fixed points of this action mod p. What do we know about the left-hand side? This subgroup is the Sylow p subgroup. So that means p does not divide the order of this set, because the highest power of p dividing G is the highest power, the order of G is the highest power of p dividing the order of this subgroup. So what does that mean? That means that p doesn't divide the right-hand side of this either. So whatever these fixed points are, p does not divide, p does not divide this number of fixed points. So what does that mean? This number of fixed points, it's not divisible, it's not 0 mod p, so it's definitely not 0. So what does that tell us? The big idea is that tells us there is some fixed points. So taking a step back, we have this action of q on the left cosets of our other Sylow p subgroup by left multiplication, and applying the fixed point congruence tells us that there is some fixed points of this action. Okay, so let's name this fixed point. So that means there is some left coset of our subgroup p in G that we can write as like the left coset of p containing some element little g. And it's a fixed point, so that means that q acting on this coset, gp, is gp for all q and q. All right, so what does that mean? Well, the action is by left multiplication, so that means the left coset of p containing q times g is the left coset of p containing g. So that's the same as saying that g inverse qg p is p, that the left coset of p containing g inverse qg is the same as the left coset of p containing 1 for all q and q. What does that mean? That means g inverse qg is in p for all little q in the group q. And that means that g inverse times the subgroup q times g is contained in the subgroup p. But now, just like we saw in the previous video, these are two subgroups, these are two finite sets that have the same size. So if one of them is contained in the other, then in fact they are equal. So we've seen that g inverse qg equals p, which means that q is gpg inverse. Q is the conjugate of this subgroup p by this element little g, and that's what we were trying to prove. So how did this argument go? We wanted to show that any two Sylow p subgroups are conjugates, so we named two of them. The big idea is to consider a group action where you take multiplication, left multiplication by one of the cosets on the set of left cosets of the other. This feels kind of clever, but if you want to do this argument with a group action, that group action should involve both the subgroup p and the subgroup q in some way. And there aren't that many different kinds of things to try. So the next big idea is the fixed point congruence. And then it just comes down to the fixed point congruence tells you that there is one fixed point. So that fixed point gives you a coset of an element in G mod P, a left coset of P in G that is kind of special. It's a fixed point for this action. So when you write down what that means, you get exactly what you're looking for. So the most important thing in remembering how this argument goes is to remember what the action is that makes this work, and then remembering to apply the fixed point congruence. So in the next lecture, we'll prove the remaining pieces of the Sylow theorem, and we'll also see a bunch of applications.